Hi, my name is Shravan.
I'm Shreyas.
My name is Gary.
Hey.
This is a local planner learning from demonstration.
So a brief roadmap of what we're talking about today. We're going to discuss some of the background, as well as the approach and the experiment that we did, and then discuss the results and our future steps. The motivation for our work stems from the fact that hand-tuning local cost function parameters is not really ideal, and that's because of two reasons. Firstly, it requires a skilled roboticist, which is mentioned in Zhang et al. And secondly, it requires many attempts for that roboticist to match a human demonstration. And even if a human demonstration is matched with parameter tuning, static navigation systems often struggle whenever they're put into varied contexts. So how do we tackle that challenge? We implement inverse reinforcement learning to produce a cost function for a local planner. And we experimentally validated this on simulation as well as the real-world clear path travel.
To discuss inverse reinforcement learning, we can briefly look at one common paradigm, which is just applying reinforcement learning for robot navigation, where we learn the correct action to take based on a reward function. However, this is often in the real-world deployment, this is often unachievable because of two reasons. The first reason being that in the real world, often the reward function is not available or unknown to the expert roboticists. And number two is in the real world, when you train a reinforcement learning model, there's guaranteed to be a numerous amount of failures, such as the robot crashing into walls, or crashing into obstacles, or performing some kind of recovery behavior. And that kind of behavior sometimes is just unacceptable, even once. For instance, you cannot have the robot crash into a wall even once, and there will be damages. And the other paradigm that we want to look at is learning from demonstration. We try to emulate a intended behavior set by an expert demonstrator throughout a certain course, or to learn a certain behavior that's been previously shown to work through a certain pattern. And in this, we have two papers we have to discuss. One is representation learning from demonstration, where we learn a representation of a certain environment, and we observe which environment was preferred by the demonstrator, and we try to match that environment as closely as possible in order to generate a path that is very, very close to human demonstration. Another one is to do parameter tuning from demonstration, such as it works in AppleD, and which we try to learn a parameter policy from a human demonstration. So in this paper, we discussed tuning the parameters of replacing the evaluator in the local planner. So what exactly is the local planner? The local planner is the planner that plans the path to the local goal, which is described as the path that is on the 1 meter circle with crossing the global path, either marked by some Dijkstra's algorithm or by some A-star planning algorithm that has a coarse goal to the end of the algorithm. And our local planner here, we use a trajectory rollout local planner, which there are three parts. There's the sampler, there's the evaluator, the executor. And the sampler just scatters some trajectories that it thinks are pretty good trajectories. And each of these trajectories can be described with three constants, which are distance from the goal, how close it gets to the goal, the clearance, how close it gets to an obstacle, and the path length, which is how far this path actually is. So as you can see, some of these paths are very, very short, and some of them are very, very long. All of these is passed to the evaluator, which picks the best one given out of these sample trajectories, and this best trajectory is then passed to the executor to generate the motion commands, such as V and omega at each time step.
So a little bit more about our actual approach. So we're trying to really learn how we want the agent to interact with, interact inside of its environment given these sort of different possible trajectories. And the goal is to find a reward function that can describe its optimal policy. So as Gary said before, by using basic reinforcement learning, we would be trying to let the agent explore its environment and learn different sort of state action pairs in order to act in a proper way and learn the reward function implicitly. But what we're trying to do with inverse reinforcement learning is sort of mimic that same learning style, except we provide a human demonstration and find the optimal policy through a reward function more directly by taking the environment as input and taking abstractions of the environment in particular as an input. So we can look at our specific application. We're taking in variables that describe the environment, so the three that Gary outlined previously. And the reason that we're doing this is instead of taking, say, the entire scan data and just using that as inputs to the model, because we want to learn off of a representation of the environment that we're working inside of, so that it can generalize a little bit better. And after that, once we take a sort of description of the current environment that the robot is working inside of. We can compute the costs for the setup trajectories given to us by the sampler at every time step. And just for context, these setup trajectories is sort of described by different constant curvature arcs, which is basically different radiuses along the circle. And we basically compute which sort of trajectory amongst those setup trajectories that is given to us by the sampler would be best. And then we output the trajectory with the lowest cost based off of what our reward function that we derive from inverse reinforcement learning gives us. So just at a higher level, the inverse reinforcement learning course that we're taking is trying to learn a reward function that describes the optimal policy from demonstration. And this policy, this function can be used to ascribe costs to different trajectories during trajectory rollout, and we can take the one with the lowest cost at the very end to describe the optimal trajectory at a certain time step. So yeah, going into the approach, this sort of gives us a visual of how inverse reinforcement learning works. We have an optimal policy given to us by an expert demonstration or human demonstration or just any other means. And we have the environment variables, C1, C2, C3 that Gary mentioned before. And we feed that into our inverse reinforcement learning paradigm to sort of describe the optimal policy in a really tactile and concrete function. So we explored three approaches. The first was based on constant curvature arcs, and here we looked to train an inverse reinforcement learning model that can directly match the hand-tuned parameters that were given to us just to determine the efficacy of implementing this sort of system given the same sort of bandwidth and space as the hand-tuned model. The second one was based on trajectory rollout index, which was the sampler gives us the set of trajectories and their index from 0 to 40, and there's sort of a constant difference in terms of angle between the different trajectories. So we can use the trajectory rollout index as sort of a discrete marker of which trajectory we want to pick, and they're very related in terms of the trajectory that's one index off or two indexes off is much closer than indices that are off by a greater margin of error. And then the final one is inverse reinforcement learning based off of the human teleop data, so actual human demonstration. And the way we do this is we convert the command val outputs to constant curvature arcs and follow a similar approach as the one done by trying to take the constant curvature arcs determined by the hand-tuned parameters. So what the hand-tuned parameter function is basically just another cost function, and that can be used to pick the best trajectory, and then using that best trajectory is described by a constant curvature arc. In the second implementation, the trajectory rollout index directly maps to a constant curvature arc because every single trajectory has a unique constant curvature arc. And then the final one is we can convert command val velocity, like the node outputs, to constant curvature arcs and use that to train IRL models on to find the best trajectory that we want to pick.
So talk a little bit about the three different approaches, the IRLH, IRLC, and IRLI, and how they apply to local planners. So we observe three different metrics that we like to measure. One is the accuracy of how close we predicted the correct one, the mean squared error, to which to signalize when it was wrong, how wrong it was, and then the left-right bias on which the machine learning model either predicted a leftward incorrect trajectory, where it was turned too far to left, or a rightwards incorrect trajectory, where it turned too far right. So we observed that the IRLH, which is the one learned from the human demonstration, converted into constant curvature arcs, and the REM that is just based on constant curvature arcs, both support very, very high accuracy with very, very low mean squared error, and always with the rightward bias. This could be the intended behavior because the human could have a rightward bias naturally driving, and that could be reflected in both these two models. The IRLI, however, has a very, very poor accuracy with 0.001. A figure, we only have 40 trajectories, so this is worse than random guessing. And the mean squared error is 0.63E7, which is 7 magnitudes above. And then every single one of them performed a leftward trajectory, and none of them performed a rightward trajectory. In this case, we would like to proceed our future work with the IRLH model or IRLC model, and we would like to forego this IRLI model, as clearly this metric of choosing the best trajectory does not show any efficacy.
All right, so there are two videos here. One is in simulation, and you can see in green the global path, and in blue you see the constant curvature arcs, which are rolled out by the sampler. And in red we have the chosen path, which is chosen by our cost function. And this is IRLC. All right, and this is the same model being deployed on the robot.
And just going back to this, so what we actually did here is that the model deployed on the robot is the same one trained on simulation, so it just goes to show how training on the sort of representations of trajectories is widely applicable. So general conclusions. We were looking at the local planner and we identified that current ways of ranking trajectories and choosing the best trajectory from the sampler requires a lot of expert intervention in terms of producing a hand-tuned cost function. So what we work to accomplish is develop an inverse reinforcement learning approach to reproduce a cost function for the local planner that can pick trajectories in a more robust way and fit to more unique scenarios based off human demonstration. And what we identified through our experiments was that IRO models are accurately able to both emulate hand-tuned navigation systems as well as human demonstrations to produce robust and sort of semantic-aware navigations.
Our next steps in this project would be adding a fourth environment descriptor to describe visual information, where we now currently have C1, C2, C3 from geometric information. We can add another constant C4 as a visual representation of the environment that we're currently in. Second one is to use a raw data from a LiDAR scan. So right now, currently we use C1, C2, C3 as previously mentioned, but those are hand-tuned parameters that expert roboticists have determined are pretty useful from LiDAR scan. And we would like to have a model learn what is useful on its own without the guidance of C1 to C3. So if we incorporate the raw LiDAR image, we're able to do that. And then lastly is to apply this to different types of planners. So for instance, we can apply it to a lattice planner, or we can learn either a control set to plan a certain lattice, the points for navigation, or we can learn how to plot these lattice points so it has the best navigation policy.
All right.
Thank you.
Yeah, thank you.
All righty. So question.